Hey everyone, welcome back to my channel where I talk about all things tech and finance, and in this video I'll be going over multi-threading and hyper-threading. Multi-threading divides your work for simultaneous processing. Your work is split into multiple chunks by threads. Your work is processed in parallel by different CPU cores, saving a ton of time. Hyper-threading allows for more than one thread to run on each core that you have. More threads is equal to more work being done. Each core accepts two threads or two specific hyperthreads. The main difference between hyperthreading and multi-threading is that hyperthreading converts a single processor into two virtual processors. This is primarily an Intel piece of technology, and hyperthreading helps increase performance of a CPU core by running multiple threads in a core. Using hyperthreading, the operating system can increase the number of instructions that it can complete and reduce idle time on different threads, alternating which tasks are done first. Multi-threading, per its name, executes multiple threads in a single processor, which leads to what we are discussing now. A thread is a virtual version of a CPU core. You can think of a thread as a program or a task. Multi-threading is a technique that allows for many tasks to be run at the same time, all sharing the same resources. Multi-threading occurs everywhere. Think in terms of Google searching through a bunch of keywords while opening a bunch of tabs or having other apps that are open on your computer. Your computer is essentially executing all these commands at once. Here, we are going to be discussing the hardware components at a very high level and how we can utilize these components for scientific computing. A socket is a physical connector that accepts a single chip. Note that this number can be greater than 1 if you have multiple sockets for the multiple or multi-core chips. In this case, I just have one physical CPU. So what is this CPU core we have going on here? This is an actual hardware component. Essentially, the more cores you have, the better you're off. Supercomputers are known to have thousands of cores in their configuration. So you can think of the core as a brain of the CPU. It receives instructions, performs calculations, and executes operations. Intel, with its hyper-threading capability, consists of 2 logical processors per core. So what is a logical processor? The number of logical processors can be computed by multiplying the number of physical cores times the number of threads per core. Since we are working with Intel technology, there are usually 2 threads per core, so I would have 16 logical processors as we see here. So over here, I actually have a package over here. I just did a question mark on for each. This is the parallel package that we'll be using just to resemble a parallelization to utilize our cores that we got going on over here. First things first, we also want to just remove everything that we have in our history and then set the seed as 1 so that if you guys want to follow along, we should have the same results more or less. So first, let us actually do a serial representation. And what I mean by serial representation is that all of our tasks are being done one after the other, and we're only doing everything on essentially just one processor. So let me actually, and in this example, I'll just be simulating a linear model where I have n observations over here, which is just I'll just be doing 10.6, which is just a million observations. Number of features, I'll be using 10. So I'll have 10 columns to play around with. And then I'll have standard deviation, which is just, I'll set that as 1. And then my beta coefficients, which would just be repetition 1 10 times over here. So let's run that. Everything is, I think I may have flipped. No, that's fine. Okay, cool. These are our variables that we'll be using to just go through the serial representation of a for loop to just run through all these models, and then we can store all of our beta coefficients into an array or a data frame. In order to do this, we're going to have a for loop for these serial representations, iterations, that's just 100. We have a start time because we always want to time this because this is like the main point of this video for serial representation and as well as a parallel process, and also we want to print out time serial, where serial time serial is end minus start, and then close the parentheses here and end that with a 3 because this is just the start time over here. Inside of, well, between the start and the end, we're just gonna have a for loop. So it'll be like for I in 1 to iterations. We'll be iterating through 100 number of times. We're gonna have 100 models. We want to store our beta hats that we are going to be generating from our linear relationships that we are going to be generating over here, and we're going to see that very soon. We have X observations, where we just have a matrix full of randomized values, where it's like n times p, lowercase p, where n is number of observations, as we see over here, p is number of columns, and we need to separate this out. So number of rows is equal to n, number of columns is equal to p. Same thing over for y, except that this is going to be the predictions that we're going to be computing due to the linear models. That will just be x, and then this is going to be the notation for the R's way of computing out matrix multiplication. So it'll be x, you multiply that with your beta coefficients over here, and then of course we need to generate some form of randomized variance, or standard deviations, I should say. And that would just be our norm of, we have n observations, we have n number of standard deviations, and we are going to put that as standard deviation is equal to standard deviation. That should be that. So once we have our x and our y values, we want to create the linear model just using the lm function and y tilde x. We don't want an intercept, although you could do an intercept on your end. It really doesn't matter at that point, but the 0 just means no intercepts are included in this model. And then we want to store the beta hats. We're just going to be appending our beta hats to each other, and we're just going to be tagging along the coefficients over here. And then last but not least, let's actually print out where we are in this process. So it'll just be a paste iteration completed at, and then this should just be I. So I think this should all run. Let's actually run this, see how long this, oops, did I miss? That should be parenthesis right there. I think that was, let's try that again. Unused n rows over here. Let's run that. Yep, okay, that was the issue over here. Okay, so that took about 106 seconds for everything to run. Now let's actually compare this to when we are parallelizing everything. So there's going to be one package we'll be using that utilizes the for each function that we got going on over here, and that is the library of do parallels. Put that in parentheses over here. Just to get the packages over there, and then we're gonna be loading that in, and then there's a really cool function we can utilize, and that's detect cores over here. And I use this all the time if I'm on different computers, but in this case I have 16 cores that I can play around with and utilize. In general, it's always good to start off with half of the number of cores that you're given with, unless you already pre-know however many cores you're going to need for your given model. But this is the case on where this is like a really nice benchmark, and also to take into consideration that if you have lots of cores, like thousands of cores, it does not necessarily mean a huge speed up when you are trying to put more cores into your program, because the number of tasks that are associated with your program, there just might not be enough to go around, and so in general the speed up might not be like a huge difference. In fact, it might be negligible. So you want to take that into mind when you're like calculating your costs if you're utilizing some form of cloud service. But anyways, let us actually register our parallel systems, our clusters. Over here, we're going to be using 8 cores. We register, should be CL over here. Did I not run this? Okay, cool. Register that. And then over here, we're just going to be doing pretty much the exact same thing. We have some iterations that we can start, and we're going to be ending with the for loop we got going on over here, except our for loop is going to be different. And so let's actually just delete this over here, and this is what it is going to be. So let's call this like beta underscore hats. Since we're working with 8 cores, we're just going to call that underscore 8. I have a for each loop, as we see on the right hand side, for each, and then we'll be going from 1 to iterations. Also, we want to set this, that's the index, 1 to iterations. We are going to be returning a let's do like our bind function over here. We are going to be returning essentially like a matrix of all of our beta coefficients as like one giant data frame. And then we are going to run this do par, which is a really neat pipe that you can use. And then essentially the exact same thing. We have our x, we're gonna have our y's, and we're gonna have our models over here. So let's copy and paste this right here, and then take that line out. Also note that printing anything inside of our parallelized for loop does actually not make sense, because the way that parallelization works is that all of our processes are just essentially running out of order, because that's like what the threads are doing. They're running as fast as they can. So there's a bunch of bit lines that are going in and out of our cores, and whatever goes first, that is essentially what is going to be run first. And so it can necessarily be taken out of like context or out of order, and that's where we're just appending everything, whatever comes first. There's going to be some slight differences in what we are working with over here. As you can see, we have beta hats, but we want to instead of just appending this value, we are actually going to be returning our beta hats, and our beta hats we'll just call that beta hats so we don't confuse coefficients or variables. But our beta hat underscore 8, let's just do that. No s, okay, 8. That is going to be the model at your coefficient, model coefficient. And this should essentially just return all of our beta hat coefficients when our for loop is running, and is running as fast as it can. We have all these threads that are going through, and this is going to be appending to our new data frame over here. And we'll see that real quick. And this should actually run really fast because we are utilizing parallelization. And last but not least, we also want to stop our cluster, C1 over here. Cluster, yeah, we want to stop that. And then I think we are good to go. Instead of time serial, we'll just have time parallel underscore 8, time parallel over here, and let us run that. Hopefully there's no errors. Okay, so it seems that is running. Let's look at our CPU utilization. Oh, a huge increase from 20% all the way up to 75-ish%. Yeah, 75-ish%. That's because since we're not going to 100, we're not using all of our cores that we are having. If I put this to like 15, it will definitely go to 100%, or 16 for that matter. But I'm running a bunch of other programs right now, and I don't want to crash anything. So yeah, that actually took 30 seconds over here. So as you can see, it took much less time compared to what we had earlier, which was like, I think it was 100 seconds. It's like 100 seconds. So huge increase. I hope that you all enjoyed this demonstration on how to utilize parallelization and appreciate the differences between serialization and parallelization, and how one is faster than the other. So I hope that you enjoyed it. Make sure you hit that like and subscribe button, and I hope to see you in my next video. Thank you so much for watching.